Welcome to this video on constructing half equations. And we're going to look specifically in this video about how we construct half equations taking place in aqueous solution under acidic conditions. So first thing is just a more general discussion that when we come to balancing redox equations, we often find that apart from the sort of main species in our equation where the oxidation number changes are occurring, we need some extra species. And the reason is that there is simply not enough of each element around. So let's take this full equation. We find that in this case we've got 8 hydrogens on the left side. There's no hydrogens on the right, so where did the hydrogen go? And secondly, in this half equation example here, you could change the numbers of these two till you're blue in the face, but there's no way that you can create oxygen on the right hand side unless you add in some kind of other species. So we need to add in another species. Now if we look carefully at the oxidation numbers, we find here that we need hydrogen with a +1 oxidation number, and here we would need oxygen with a -2 oxidation number. So we need to think what species will be formed in each of these reactions which we have hydrogen as +1 and oxygen as -2. Now we might think, oh, hydrogen gas, what about that? The only problem here is that actually this would be oxidation number 0, so that can't be right. The only thing that's going to be decreasing in oxidation number here is actually the nitrogen. You can't have more than one element that decreases in oxidation number, and therefore we can't use H2. We need something where hydrogen is in the +1 oxidation state. And similarly here, we can't just use O2, because again that would be in a 0 oxidation state. So we're going to be saying, even though this is actually supposed to be a half equation where only one species can be oxidized or reduced, you can't have O2 in here as well. And so what we need is a species that will work, and the answer is that when we're working in aqueous solution we need to use H2O, which is, if we assign oxidation numbers, hydrogen in the +1 oxidation state and oxygen in the -2. So this works really, really nicely. Now the other species that we can invoke is come from the idea that water actually ionizes itself. So we can simplify what that's going to form to say that water forms H+ and OH- ions. And that is not a redox process, it's an acid-base process where we retain exactly the same oxidation numbers in so doing. Now when it comes to neutral solutions, then we have actually got very, very low concentrations of H+ and OH-. But if we're in acidic conditions, we've got abundant H+, whereas if we have alkaline conditions, we have abundant in alkaline conditions, abundant OH-. And water is always going to be present in aqueous reactions. Now it may not always be the case. There are situations where this isn't going to arise, but most of the situations that you get in A level are aqueous, and therefore we can use water and H+ or OH- to balance the hydrogen and oxygen. And it's important that we understand we're always going to be using water because there's always an abundance of it, and it's either going to be H+ or OH- depending on the conditions that we face. So that said, let's have a go at trying to see if we can construct some half equations. So in this case we've got acidic conditions. Zinc is reacting with sodium dichromate to make Zn2+ and Cr3+. So the way we're going to do this, we've got our two half equations, one for oxidation and one for reduction. And the first thing we do is we insert the formulae of the main species in these equations. So we're going to have in the oxidation half equation Zn and Zn2+. And then we're going to balance the atoms. And in this case that's actually already done because we've got one zinc on the left and one on the right. And then we're going to balance the charges and crucially here we're going to be using electrons in order to do this. So if we change the charge on the left hand side is 0, the charge on the right is 2 plus 2. Electrons can only decrease positive charge, so there's no use in adding any on this side. We need to get this down to 0, and the way we do that is by adding 2 electrons. Well, hopefully you're starting to see the idea. Why not pause the video and see if you can see what happens to the dichromate. Well, again, we're putting in our key species. Now, in these reactions, we can often just use an ionic equation, pretty much always, because it's sodium never ever changes oxidation state. We know that it's the dichromate because the chromium is what forms chromium 3 plus versus in here it's chromium 6. So we can just stick dichromate in the equation. We need Cr3 plus in there as well. Now we're going to balance the atoms. Now, first thing to see is that we've got 2 chromiums here, so we need a 2 in front of that. Second thing is we've now got 7 oxygens on the left, so we're going to need 7 H2O to get them. That means we need 14 H plus in order to balance out the hydrogens. So then when it comes to balancing the charges, we can notice here that on this side we have a total charge of 12 plus. On this side we've got a total charge of 6 plus, so the 12 plus needs to be lowered to get to the 6 plus, so we need 6 electrons. And that is something that you can just confirm and check when you've done that the oxidation numbers bear it out. So if we look at the chromiums here, they're both plus 6. These chromiums are here are plus 3. So we've got a total decrease here from 12 to 6, which means that we need 6 electrons, remembering that each electron essentially has an oxidation number of -1. Well, here's another example for you to try. Pause the video and see if you can do this one. Well, I wonder how you got on. So let's run through the same method. We're going to insert the formulae of the main species. So in this case, for oxidation, it's the cobalt, which is going from cobalt 2 plus to cobalt 3 plus. That's actually already balanced in terms of atoms, and so we're just going to balance with charges. We've got 2 plus on the left and 3 plus on the right, and so we need an electron on the right hand side so that we get a charge of 2 plus and a charge of 2 plus. Reduction, a little bit more difficult. The ferrate ion, FeO4 2 minus, and that is going to form Fe3 plus. Again, we do the atoms first. The ions are balanced. We need to balance out the oxygens, and our go-to species for that is water. So we're going to make 4 H2O because that's got 4 oxygens in. We've now imbalanced the hydrogens, but it's no trouble because we simply add 8 H plus on the left hand side in order to balance. So now the atoms are balanced. We do the charges. We've got a total charge on the left hand side of plus 6. The total charge on the right hand side is plus 3, so this needs to drop to plus 3. We need to add 3 electrons. And if we look at the oxidation numbers just to confirm that that's okay, we've got plus 6, plus 3, so we're expecting 3 electrons. And that's how we construct half equations in acidic conditions.